Welcome to This Explainer. Today, we're diving into a literal microscopic detective story. We are on the trail of a fleeting molecular fugitive, something that's been evading scientists for decades. And its recent capture? Well, it's completely rewriting how we think about the building blocks of futuristic materials. Let's get right into it. So, what exactly happens when a molecular sandwich starts to slip? I know, it sounds a bit absurd, right? But this bizarre question is at the heart of a fascinating discovery straight out of the Okinawa Institute of Science and Technology, or OIST. And the answer is fundamentally reshaping our entire understanding of ligand dynamics and organometallic chemistry. Section 1. Meet the molecular sandwich. To really understand this mystery, we first need to meet our main suspects, metallocene. Discovered back in the 1950s, these things are basically incredibly elegant microscopic sandwiches. Picture this. The meat right in the middle is a single transition metal atom, and the bread holding it all together is made of 2 carbon rings, typically cyclopentadienyl ligands. The metal coordinates equally with all the carbon atoms in these rings. This unique structural design was so revolutionary, in fact, that finding one famous version of it, called ferrocene, helped earn its discoverers a Nobel Prize in Chemistry in 1973. Now, these aren't just theoretical doodles on a chalkboard. They are very real, very stable compounds. On screen, you're looking at actual crystals of these complexes isolated in the lab. One's a stunning yellow, the other orange. These vibrant crystals are the physical evidence of these microscopic geometries. Capturing them in a solid state like this is a real game changer, because it allows chemists to analyze their exact atomic arrangements using structural chemistry techniques. Section 2. A long-standing chemical rule. For decades, these sandwich compounds have been the good guys. They've obeyed a very strict set of laws and behaved in highly predictable ways. And the absolute most crucial point here is the number 18. In organometallic chemistry, there's a fundamental principle about stable transition metal complexes. Basically, the rule states that they typically contain exactly 18 electrons in their valence shell. This gives them a highly stable noble gas electron configuration. Think about the orbitals for a second. You've got 1 s orbital, 3 p orbitals, and 5 d orbitals. That is 9 valence orbitals in total. Since each one holds 2 electrons, nature just really prefers to fill them up to exactly 18. Chemists have treated this 18-electron rule as the ultimate baseline for how these molecules stabilize. But you guessed it, here is exactly where our mystery begins. The organometallic chemistry group at OIST, led by Dr. Satoshi Takeabayashi, wanted to purposefully break this rule. Their goal was to push beyond the limits to create unusual, highly unstable 20-electron derivatives. Now, they'd actually pulled this off before using iron. But ruthenium, that's a heavier, more complex 4D transition metal. It has more diffuse orbitals and completely different steric and electronic properties. So when they ran the experiment hoping to create a 20-electron ruthenium derivative, the reaction completely collapsed. Instead, they unexpectedly produced standard, perfectly normal 18-electron products. Literally, a chemical reaction meant to break the rules resulted in the standard thermodynamic outcome. The big question was, why? Section 3. Catching the hidden state. So how did a radical, rule-breaking reaction just fizzle out into perfectly normal products? To find out, the researchers had to ask a really tough question. How do you study an intermediate state that disappears almost instantly? You see, the secret to their failed experiment was hiding in the shadows between the start and the end of the reaction. These intermediate stages are fleeting, kinetic states. They exist for just a fraction of a second before vanishing into that final, stable thermodynamic product. They're notoriously difficult to observe, simply because they don't stick around long enough to have their picture taken. To catch this molecular fugitive, the team brought in the heavy machinery, an impressive suite of high-tech detective tools. They combined single-crystal X-ray diffraction to capture the solid-state structure, NMR spectroscopy to understand how it moves in solution, mass spectroscopy to confirm the molecular weight, and advanced computational modeling to map out the transition states. They basically threw every analytical capability they had at this reaction. And this incredible synergy of techniques allowed them to meticulously map the entire chemical pathway and, amazingly, freeze and isolate that highly unstable intermediate. And when they finally captured this hidden fugitive, the results were absolutely stunning. Dr. Takeabayashi noted, "We were able to isolate an intermediate structure. Surprisingly, we found the structure to be doubly ring-slipped. Think about that. They didn't just find a normal stepping stone, they uncovered an entirely unprecedented structural configuration, hiding right there in the middle of the reaction. Section 4. What is ring slippage? Now you might be wondering, what exactly does it mean for a molecule to slip? Let's break down how this builds step by step. In step 1, normal bonding, the metal atom is perfectly sandwiched, coordinating equally with all 5 carbon atoms in the ring. In chemistry, this is known as an eta-5 bond. But then, in step 2, a single ring slip happens. One ring shifts its grip to stabilize the electron count, altering its hapticity. And finally, step 3, the double ring slip. Both carbon rings partially detach, dropping all the way down to a rare, precarious single carbon connection on both sides. That's an eta-1 bond. The molecule literally alters its own coordination geometry on the fly just to deal with the excess electrons. This is a massive milestone. What we're looking at is the very first time a double ring slip sandwich intermediate has been fully characterized at the molecular level. Catching the structural deformation right in the act is a massive first in chemistry. It finally gives us a clearer empirical picture of exactly how these complex organometallic molecules assemble, dynamically rearrange their connections, and break apart during catalytic cycles. Section 5. Futuristic materials and beyond. But okay, let's step back for a second. Why does catching a microscopic slip-in sandwich actually matter to us in the real world? Well, because metallocellines are fundamental building blocks. They are absolutely essential for creating new industrial catalysts, advanced energy technologies, sophisticated sensors, and even targeted drug delivery systems in medicine. When a ligand slips from eta-5 down to eta-1, it suddenly opens up coordination sites on the metal center. By finally understanding how these carbon rings slip and shift around, chemists can design highly tunable structures. We can exploit those open coordination sites to create materials and catalysts that respond perfectly to specific chemical stimuli. It's like finding a hidden control panel for chemical reactions. Which leaves us with this final, really provocative thought. If we can now control how molecular sandwiches slip and deform, what kind of futuristic, shape-shifting materials will we build next? Now that we can actually see and understand the hidden slips of these molecules, the possibilities for next-generation chemistry are wide open. Thank you so much for joining me on this explainer, and remember to keep questioning what's hidden right in front of us.